So till last class we were looking at different new kind of things. So we were looking at totally different things like how to generate measures and sigma algebras, right? So we were looking at how to generate measures and sigma algebras. This is what we have been doing. So from now onwards, we are going to look at new aspects, what is known as our aim. So the course, the title of the course is Measure and Integration. So we wanted to do integration. So in order to do that, the fundamental concept that is expected is what is known as the so-called measurable functions. Right. So, well, so this you must have seen in your so this you must have seen during your real analysis, but let me just put it as an exercise, because this is going to help you. Yes. So let f from omega to omega dash be any function.
I haven't shared that.
I have shared. Is it visible to all? Is it visible?
Yes, sir.
Yes.
Okay. Yeah, you choose any function, then, well, why should I write this? Prove the following. First one, f inverse of union is equal to union over union of f inverse. Second one, f inverse of the intersection is same as intersection of the f inverse. Third one, f inverse of the complement is same as complement of the inverse. Right. Yeah, this you must have seen in real analysis. So I've given it as an exercise, and in fact most of you have used it in the minor. So at least good that you all know that all these are true. Fine. So now second thing is that, well, this was again part of your minor, but again let me give it as an exercise, and most of you have done it. Let f from omega to omega dash be a function and let a dash be a sigma algebra of subsets from omega dash. Now let A equal to all those E subset of omega such that E is of the form f inverse of E dash. Well, I'll write it as all those f inverse of E dash such that E dash belongs to E dash. So show that A is a sigma algebra. Right? I believe that most of you know the proof, and I've seen that many of you have done the proof correctly. Very good. Right. Right. So there are two things. One is, if you have omega 1 A1 and omega 2 A2, these are two measurable spaces, and if I have a mapping f from omega 1 to omega 2, there is a, now this f induces a, implies f induces a natural sigma algebra on omega 1. That's what we saw. So now there are two sigma algebras. One is A1. This is the given sigma algebra. And well, I'll write it as AF. This is the sigma algebra induced by F. Right. So there are two sigma algebra. So natural question is, what is the relation between these two? In fact, are there any relation between these two? The answer is, in fact, there is no relation in general. So in general, there is no relation between. Right. So let me begin with a definition that let omega 1 A1 and omega 2 A2 be any two measurable spaces. And let f from omega 1 to omega 2 be a function. We say that f is A1 A2 measurable or measurable with respect to A1 A2 if f inverse of E belongs to A1 for all E coming from A2, or equivalently this AF is contained in A1. Right. An easy exercise here is the following. Show that composition of measurable functions is also measurable. Right. So suppose that you have a function f from omega 1 to omega 2. Of course, omega 1 and omega 2 are measurable spaces. These are measurable spaces. Fine. Now, if I know that A2 is given by, it is generated by a subcollection E2. For example, R is generated by, it's a sigma algebra generated by all open intervals. In fact, right? So this much is known to us. So in that case, is it enough if we can verify only for the subcollection? So in order to verify whether f is measurable or not, is it enough to verify the same, whatever definition, same for the subcollection E2? In fact, the answer is provided by the following lemma. Let omega 1 A1 and omega 2 A2 be measurable spaces and let f from omega 1 to omega 2, sorry, yeah, so we'll have this omega and let me say that A2 is given by sigma of E2, right? So it's a sigma algebra generated by the subcollection E2, right? So if f from omega 1 to omega 2, then f is A1, A2 measurable. If and only if f inverse of E belongs to A1 for all E coming from E2. Yes, so it's enough if you can verify it only for E2. Yes. So which way is the proof easy? Which way is easy? Forward part, backward part?
Forward.
Sorry, I couldn't hear. Please be louder.
Forward part.
Right, forward part, right. Why is this forward part easy?
By definition, that f is measurable, so we know.
Exactly, right. So once you know that f is A1, A2 measurable, f inverse of E belongs to A1 for all E coming from A2, in particular for E from E2. So I'll simply say forward part is obvious. But do not write it as obvious, at any cost. Right, backward part. Yes, how do you prove the backward part? Right.
We can take an set in sigma
Huh?
E2 and
Sigma?
we can take an set in sigma E2 and then we can write as union of the elements in E2
How
and
do you
then
know
using
it is a union?
because it belongs to sigma algebra generated, right?
But how do you know that it is only in the form of union?
Sir, it will be in the form of union, intersection, and complementation. But since in taking inverse of a union,
But
intersection,
all
or
these will not
complement
help.
is
Huh? All these will not help. Right. First thing, look at all those E subset of Y such that F inverse of E belongs to A1. Yes. So what can you say about this one, this set? This collection. Right. So I'll simply say that verify that this is a sigma algebra. Yes. So I'll give you 2 to 3 minutes time. Start verifying it. If you have verified, just raise your hand. Verify that this collection is a sigma algebra. Start. Is it done? If you have verified, please raise your hand. Yes, others. Others, please. Bishwa Prakash, Devranjan, Manoj, Preeti, Bishwa Prakash.
Yes, sir.
Okay, fine. No problem. Manoj, Manoj.
Yes,
Have you finished it?
finished.
Okay. Preeti, Preeti. Fine. So now let's proceed further. So this collection, this is a sigma algebra, right? Second thing. So what can you say about this sigma algebra? What can you say? In fact, this is a sigma algebra on omega 2. Yes.
This contains the collection E2.
Ah, right. So this sigma algebra contains E2. Yes. And therefore, the sigma algebra generated by E2, which is A2, is contained in all those E subset of Y such that F inverse of E and right. That means what? The sigma algebra AF is contained in A1 implies F is measurable. That's it. Right. So as an immediate corollary, we have an important statement. What is that? Let omega 1 tau 1 and omega 2 tau 2 be topological spaces. And let f from omega 1 to omega 2 be a continuous function. Then fs b tau 1 b tau 2 measurable. Yes. So what is this b tau 1 b tau 2? What are they?
The Borel sigma algebra.
These are the Borel sigma algebras generated by tau 1 and tau 2 respectively. Yes. Right. So in the case of R, we have various sigma algebras. Sorry, we have the Borel sigma algebra and it is generated by various collection. Right. So if f from omega comma a, a to r. Well, so I'll not mention with respect to which sigma algebra the function is measurable because it is understood from the context. I'm not going to specify it again and again unless and until there is a need. If this is measurable, well, sorry. Then the following are equivalent. Fs measurable, F inverse of the open interval belongs to A for all AB in R. Third one, F inverse of open A close to B belongs to A for all AB in R. Fourth one, F inverse of other way, close to A open B belongs to A for all AB in R. F inverse of close to AB belongs to A for all AB in R. Of course, there are a few more which I don't want to write. I'm just putting a dot so that you all can finish it. Fine. Correct. So, next definition. We say that a map F from omega comma A to R or C is Borel measurable if F is AB measurable. So, this Borel measurability is one of the important concepts and we are going to use it again and again in several places. Right. So, first exercise. Maybe I'll put it as a corollary. A function f from omega comma a to c is Borel measurable if and only if real part of f and imaginary part of f are Borel measurable. If these two are Borel measurable, then this is equivalent to saying that the function f is Borel measurable. Right. Well, the function f is Borel measurable, that is with respect to C. Borel measurability there is with respect to C. Here real part of f and imaginary part of f, these are Borel measurable with respect to the Borel sigma algebra on R. The next one, if f comma g from omega comma a to c, if these are Borel measurable, then so are f plus g and fg. These two are also Borel measurable. Well, as a result, what do we have? The collection of all complex Borel measurable functions form a C vector space. So what is a vector space? What is a vector space?
Sir, it is a triplet of with one set and two operations, such that the set with addition forms an abelian group, and with respect to multiplication, with respect to scalar multiplication, the distributive property holds.
But there is a small change that the set should be non-empty, which is very important. Right. So usually in the case of measure and integration, especially in this theory, one considers what is known as extended real line. R bar, which is R union minus infinity comma infinity. So on this R bar, there is a natural sigma algebra. So let me call it as BR bar, which is all those E contained in R bar, such that E intersection with R belongs to BR. So I'll leave it as an exercise that show that BR bar is a sigma algebra. Right, so this sigma algebra is called as the Borel sigma algebra on R bar. Right. Right, so whenever we use R bar, then which means that we are using this Borel sigma algebra, that is BR bar, right? So we'll not mention, right? Lemma if Fn n in n is a sequence. So of r bar valued Borel measurable functions on omega comma a, then so are the following functions. First one, supremum. Second one, infimum. Third one, lim sup. Fourth one, limins. Right. Okay, so how to prove this? How to prove these?
Sir, sir, what is omega and a here?
Oh, Fn's are defined on omega, and A is the sigma algebra on omega.
Okay.
These are functions defined on omega, and A is the sigma algebra and omega on omega. Yes. So how do you prove this? First thing to be observed is that, so note that it is enough to prove only one. Why? Why is it enough to prove only one? Why is it enough?
Because infimum can be taken as supremum of minus fn's. And
Right.
lim sup and limin can also be written in the form of supremum and infimum.
So lim sup and limins, they are by definition they are defined in terms of supremum and infimum. And infimum you can see it as minus of the supremum of supremum of minus fn. Right. Fine. Yes. Now how do you prove the first one? So let's start with let G equal to supremum over n in n Fn. Right. So let me define G as this. Right. So we'll have to claim that G is measurable. Yes. How do you show this? But this you'll have to show that this is measurable with respect to the Borel sigma algebra on R bar. Right. How do you show this? Well, again, observe that this Borel sigma algebra is generated by a comma infinity such that a in R. Is that fine? Is this correct? I've returned something, but is this correct? Then I'll simply say verified. Huh? Not a difficult one. It requires a minimum set of patience to verify it. Right. Right. So once you have observed this, then now how will you prove this? So let A belong to R. Then what we wanted is G inverse of A comma infinity. Yes. What is this set? What is this set? Well, what is G inverse of A comma infinity? Well, if you have a set, any function, what is G inverse of, well, G from, let's say, X to Y, and I have B subset of Y. What is G inverse B? What is G inverse B?
All those numbers of x which map to which are
those X and X such that Gx belongs to B. Right. And therefore, what will be this one? This will be all those X and omega such that Gx belongs to A comma infinity, which is same as all those X and omega such that Gx is strictly bigger than A. How do you write this in terms of fn's? Only then it will make sense, right? You need a connection between G and Fn. How is this G defined?
At least one of the Fn should be greater than
Huh? Can you be louder?
A. At least one of the Fn should be greater than A.
Why should that happen?
G is supremum of
Why should at least one Fn?
because G will be then greater than or equal to that F.
Yes.
So it will be greater than A.
So in fact, so this is going to be union over n and n, all those X and omega such that Fnx is bigger than E. So if one of the Fn's is bigger than A, then Gx is going to be bigger than A. If Gx is bigger than A, I'm not saying A, it is strictly bigger than A, and therefore you will have at least one Fn which is bigger than A. So let's say that it is Gx is some B which is strictly bigger than A. I cannot have all the Fn's to be lesser than A. That cannot happen. The maximum that you can expect is only A in that case. But A is not, we are not interested in A. We are interested in something which is bigger than A. Therefore, the only possibility is that it should be strictly, you need at least one Fn which is bigger than A. So which is same as union over n in n. And what is this set? This is Fn inverse of A comma infinity. That's it. And what can you say about all these Fn inverse of A comma infinity?
They belong
They belong to
script A.
script A. That's it. So since Fn's are Borel measurable, it follows that Fn inverse of A comma infinity belongs to script A for all n in n. So this implies that union over n in n, Fn inverse of A comma infinity belongs to A. That means that is this G is Borel measurable. That's it. That's what we wanted. Right. So I'll stop here. I don't have much things to do in the context of measurability. I have only very few things left out to do, which I'll finish it in the next class, and then we'll go to convergence. Right. So let me stop here.